Hello everyone, this is Dipankar Pal here. Today we are going to kind of talk about how to correlate structural mechanics with machine learning. Of course, there are many ways in which it has been done in the literature, and mine is another way of doing it. One of the things which we will learn today is basically how to capture the essence of traditional numerical methods as it relates to finite element methods, and how machine learning could help accelerate uh, that aspect. In addition, we will also try and learn basically how some aspects of constitutive modeling could be made much better using these machine learning methods and whatnot. So to start with, in this lecture, I will try to first try and understand if we are getting everything in terms of what we actually want to capture within this talk today with respect to machine learning aspects and with respect to finite element method aspects, how to correlate them, kind of give you a primer what we are going to cover in the next few talks with respect to correlating machine learning and finite element methods, if you will. Again, my name is Dipankar Pal. I work for a company called ANSYS, which is a leader in structural simulation and simulation in general. Basically, with the advent of our Pythonic interfaces, in addition to our traditional tools, it has been very, very easy now to connect to the code solvers using different methodologies. Of course, code solvers always have very high regard with respect to the kind of problems they can solve. But correlating these solvers with easier interfaces is always an aim which we like to do. And of course, for prototyping and in order to understand new physics, always going through the Pythonic interface route is a um, much easier thing to do. So in order to do that, this has been some time. I was absent because of some family medical issues that I was not able to be present during these lectures and things. I was not able to present these talks. So a lot of people actually contacted me from both industry and academia to kind of restart this course. And I apologize that it took me such a long time to kind of restart this course in ways, if you will. So let me share my screen. And since I'm doing it after a long time, it may not be, uh, you know, you know, may not be as smooth to start with. So I beg your pardon in that respect. And let's see. So I hope and believe that my screen is now getting shared with you all. So yeah, so for most of the talk today, we will be using um, I beg your pardon if my mic is working or not. I need to find that. Uh, I feel, yeah, it's working on my other machine somehow. I feel like it's working just fine. Okay, let me do this again. Okay, let's see if this. Okay, let me mute my other mic. Okay, All right. So, so I hope I'm visible on my current computer now, and now I'm going to share my screen. Okay, share screen. Okay. All right. Uh, Sharing screen, and then I go to Remarkable app, and just to get a feedback whether things are happening in a smooth way or not, I'll go to my LinkedIn profile and try and see if things are working. So it's difficult to see at this time, but I hope things are working. If not, just send me a text message, and I should be able to see it clearly. There is definitely a bit of lag in between what I can see and what I'm not able to see, but hopefully it won't matter. Okay, so so let's kill this, but and all right. So of course, let's kind of go through what we are going to cover today. So what is the primer? Oh, sorry. So primer for this talk. So the primer for this talk is basically to cover two aspects. First is how constitutive modeling can be helped using constitutive modeling, and let's say this modeling part can be better done using neural networks. So hopefully we can talk about this aspect where we talk about, instead of a relationship in between sigma and, let's say, as simple as that, it could be E epsilon, where sigma, your stress and strain are correlated. Instead of doing that, maybe, and this is this easiest form of linear elastic law, which we know about. But let's say the material law, instead of doing this particular type of relationship or any analytical type of relationship, uh, we can give this a function of epsilon dot, and whatnot. But all these correlations, if they can be done in terms of a neural network rather than in terms of explicit laws or equations in which stress and strain are correlated, for example. Um, so this is one of the parts which we'll talk about, specifically for crystal plasticity, where basically, let's say, as a function of orientation, um, you know, if we have stress strain relationships, at the end of the day, we can figure out, as a function of your orientation one, orientation two, if we have a myriad of experiments, if we have myriad of synthetics simulated correlations or synthetic simulated um, stress strain curves, volume average stress strain curves, for example, then as a function of different orientations, uh, how the weights and biases of a neural network can be uh, uh, can be captured, and then basically how you can take automatic gradients in order to kind of figure out what is uh, how, for example, d sigma, how, for example, it changes as a function of orientation, so to speak, or higher orders of orientation, for example. Then you can do similar things with respect to initial hardness, hardness modulus, final hardness, things like that. So different parameters of crystal plasticity, for example, for if we can if we can have enough number of relationships which correlate stress and strain, then we can correlate um, their responses in terms of we can figure out their sensitivity parameter with how what is the sensitivity of, for example, the volume average stress with respect to orientation, how much, what is the uh, uh, what is the significant what is the sensitivity with respect to initial hardness, what is the sensitivity with respect to hardening modulus and things like that. So yeah, that all could be done. Another important aspect is basically the aspect of stiffness learning. So so there are various methods in this regard. One of the methods which has gotten a lot of limelight in the past is called transfer learning. So basically, in transfer learning, what you do is, and this is a multi-scale method everybody keeps talking about. So basically, what you do is, for example, for people who know, let's say you have a RVE model or a representative volume element containing one type of microstructure. Then you have a representative volume element containing other type of microstructures and things like that. So basically, let's say you have n microstructures, and then as a function of those n microstructures, let's say you have different either tangent modulus, effective tangent modulus, or for example, uh, effective c values or effective tangent modulus for each of these representations from 1 to n. Then basically what happens is that as a function of these representative RVEs, instead of doing, let's say, an interpolation with respect to these RVs when a new RV come into picture, which the model has never seen. Uh, Instead of doing, for example, a regressive type of modeling, it will do the interpolation of that stiffness matrix using that neural network. So basically, as a function of these different RVs, you'll get a C effective value as a function of microstructural parameters and things like that. And then if, for example, there is a new RVE, new representative volume element, then you don't have to recompute the effective tangent modulus or effective modulus while you have to update your K matrix in the nonlinear regime or linear regime based on based on recomputing the entire RV using finite element, but you will just interpolate the effective C matrix using this neural network method. So this is pretty popular in multi-scale aspects. But what we are going to do is a little bit different compared to what transfer learning kind of says. So basically, in transfer learning, we don't go back to that particular RVE. So for example, when we were talking about the previous one, so for example, for this new RVE, we don't necessarily go back and figure out whether the C, the generated C for this uh, finite for this new RV, the effective uh, C modulus for this RV kind of you know if you do the entire recomputation of this tangent modulus, whether first of all you'll get the same C effective or not. So we don't do that
computation. And the second thing which we don't do is basically we don't necessarily, satisfy the equilibrium in order to get that C effective matrix at the first place. So it is kind of assumed that the effective C matrix is actually interpolated correctly, and it captures the equilibrium correctly as well. So the assumption of this transfer learning method, so to speak, is that not only you can interpolate the effective C modulus based on these n representative volume elements correctly, and to the next length scale as well, but on top of that, the equilibrium for the new RV is already satisfied, and the C effective or the new effective modulus, which you have to pass to the next length scale, um, appropriately has the microstructural length scales effective modulus correctly captured, and the equilibrium also is correctly captured, and the interpolation function is also correctly captured. So there is a lot of capturing going on with respect to these transfer learning type of methods. What we'll be doing is a bit simpler. What So basically, what we'll try to do is, instead of doing that particular aspect, this is what I'm drawing over here is a brick element, nothing to do with the microstructure so far. But for example, if we have this um, one brick element, just giving an example out here, um, then there are certain properties with respect to the K matrix which it will form based on the material law, of course. As simple as that, it is B transpose C B dV. So basically, the K matrix, first of all, just for simpler purposes over here, will be symmetric in nature. So that's the first property. Then it will have, for each of these nodes, there are three dots. So basically, it will have 24 cross 24. So basically, when you assemble matrices, it becomes sparse, but by itself, the element is pretty dense. So basically, it'll have a dense 24 cross 24 key matrix. And then on top of that, there will be another aspect. So first is symmetry, second is this dense matrix. Then you should be able to do Cholesky, and generally the uh, first six modes or the first six eigenvalues of of this K matrix should go to zero, right? So basically, that's what this code should do. Ideally, in terms of basically how you would like to incorporate aspects of machine learning in there, is that as one simple example is basically, let's say you have all these nodes, 1 2 3 4 5 6 7 8. So if arbitrarily you generate the data in a way that, if, for example, we are interested in element shape, and as a function of change of the the position change of the position of element of node 1 in this particular element, node 2 in this particular element, node 3, node 4 in this particular element, or 5 to 8 in this particular element, as a function of change in position of this change in position of these nodes as a function of this element, the stiffness matrix will change. Now the thing is, you can generate that database first, where synthetically you capture using finite element method how the stiffness matrix will get formed. So there will be n number of uh, n number of permutations and combinations as a function of change of the position of these particular nodes, how your stiffness matrix will change. You can calculate this using FEM. And then on top of that, uh, then you can fit a machine learning model to it. So if you have enough data, if you randomly change the position of, let's say, node 1, node 2, node 3, or combinations of those in different ways, then at the end of the day, what you will obtain is that you'll have a big database of these 24 cross 24 matrices. And basically you'll have this k matrix as a function of change of position, for example. Then on top of that, you can incorporate aspects of orientation in crystal plasticity, initial hardness, different other aspects. So those will also change your K matrix as a function of material properties. So generally, if you capture the material property well and shape of the element well, then you don't have to go through that DOF loop where basically you have to calculate k as kij in a for loop, double for loop, for example. And that computation of doing it using uh, you know using finite element can be actually uh, replaced up to a very close approximation using machine learning. So basically you will create this synthetic k matrices as a function of change of position of nodes of that particular element, or material property of that particular element, and you will create this huge database where every parameter of interest has been changed accordingly. And then basically you will capture the essence of how the k matrix is changing as a function of that particular change. So let's say for simplicity, we take this to be linear elastic problem to start with. And if you just change the the position of these nodes, either in combination with other nodes, or simply by themselves, then you will create a big database. And then as a function of that big database, you will calculate a new k. Now, one of the things which you have to remember is 24 cross 24, for example, for this brick element is 576 number of components in the matrix. But because of symmetry, uh, you will have 8, 7. You can just capture the upper triangular matrix, and that will result in 300 entities and not 576. So basically, you'll have to do your while you're training your machine learning model, instead of training for all 576 entries as a function of change of nodal position, so to speak, you can just concentrate on the upper triangular 300 entities, because the matrix is symmetric in nature. The other thing this element should be able to do, or I call it the MLEM, or the machine learning element method, is basically you know instead of from finite element method being able to take Cholesky, or ensuring that the first six eigenvalues of that particular matrix are zero or close to zero. This machine learning element method should have a way, and that goes into the IP kind of thing of answers what we are trying to do out here, that the first six modes of that K matrix from machine learning becomes automatically equal to zero. So instead of doing it using finite element method, we should be able to also do it using the machine learning element. Once that machine learning on those 300 entries is covered, then basically you should get uh, similar eigenvalues. And on top of that, not only similar eigenvalues, you should also get um, the the same uh, the same key matrices to start with. The upper triangular matrices, whether you are employing a finite element method, or you're first trained the machine learning on those synthetic quantities, and then you're creating your new machine learning element. For example, those 300 entries should be very, very similar. On top of that, they should be the difference should be very, very minimal, of the order of 10 power minus 12, 10 power minus 13, those smaller numbers, so to speak. Then, or whatever threshold you're choosing. Then on top of that, there should be automatic criteria that the six eigenvalues which come not even if we make the matrix coming from the machine learning training, the stiffness matrix to be very, very similar to finite element method, that's not a guarantee that it has the ability to have a symmetric positive definite. For simpler examples, when you're not taking friction and other things into account. But even if we take friction and other things into account, for the unsymmetric part also, we should have similar kind of things. So not only that, from finite element part of the problem, we get six eigenvalues going to zero, but from machine learning part also, we should have all the first six eigenvalues going to zero. That should be automatically satisfied. And then once you have that's those eigenvalues getting satisfied, the symmetric nature of the matrix is accurate. The values of the stiffness matrices are very, very similar in the finite element part and in the machine learning part. Then effectively you will have a machine learning representation of this particular element. So instead of using, for example, solid 185, you can use this machine learning element for quicker computation, and you don't have to go through that dof I, dof j kind of a loop. You get the full matrix in one single chunk. So that's kind of where we would like to go with respect to that. And then then the other thing is, so basically if you're plotting KFEA with respect to KMLEA, um, those 300 entries should remain on this 45-degree line, meaning that you have the same matrix. Then you have to go through the eigenvalue thing. And then, for example, if you're solving one simple problem with that new matrix, so let's say a very simple one element problem with that new matrix, where you're pulling on the top surface in the z direction, kind of arresting the displacements on this node, kind of arresting these other nodes in x and y direction. Then basically, whether you solve the problem through the finite element method or through this machine learning, a stiffness matrix coming from the finite element method or a stiffness matrix coming through the machine learning method, the other thing which needs to be captured is that the displacement using the FEAK and the displacement using the MLEAK should be again on this 45-degree line. And if these two criteria you are getting, then basically what it says is that now, whether you are getting this matrix from using finite element analysis or you are getting this matrix using machine learning enabled analysis, both of them have similar behavior. We are not only checking for interpolation, we are actually checking for equilibration in terms of getting actually the correct displacement from machine learning problem. We are also checking whether our eigenvalues, the first six eigenvalues, are going to zero or not. And then we are automatically taking into account the aspect of symmetry wherever symmetry applies. For most of the cases in engineering analysis, symmetry applies, except for certain frictional cases where there will be unsymmetry and stiffness matrix. Also, there are some magnetic materials where there will be unsymmetry because of this issue. So that is what we'll try to capture using a very simple, machine learning enabled analysis. How the stiffness matrix looks like, whether the stiffness matrix has the same values with respect to its machine learning counterpart or not, and of course, whether the finite element displacement is equal or very near equal, that everything is laying on that 45-degree line with respect to machine learning enabled analysis. After that, the other aspect which we would be capturing, so this will capture using first simple, one one element elastic material followed by its crystal plasticity counterpart. But to keep things simple, first we will do it for uh, one element elastic problem, linear elastic problem, followed by its crystal plasticity counterpart. Also, the other aspect which we will do is that after ensuring that this gives correct displacements for a bunch of elements, for example, in the RV analysis, this part will also go into the training, like the difference between the finite element displacement compared to machine learning enabled stiffness. Of course, since we have taken symmetry and eigenmodes into account while construction of the matrix. So basically, when you do even so, this is same scale analysis which we are talking about here. Basically, whether we can capture the displacement through machine learning uh, as accurate as finite element or not. But apart from that, also it has multi-scale implications, because once we can capture these stiffness matrices very accurately, as you will see you know in the talks in the later on talks, that if you can capture these matrices accurately with respect to their symmetry, with respect to their eigenvalues, and with respect to whether they after equilibrium they give the correct displacements both at the single element level and at the global construction of element level, then the next thing we'll look at is the multi-scale implication and constructing the C effective from that perspective, rather than assuming an interpolation. So, of course, interpolation is very easy and it gives you results very soon. This is a bit longer method, but it kind of enables and ensures whether your stiffness matrix has the necessary properties which makes it go on to the next level. But once your machine learning, so basically to train the machine learning method, the number of synthetic values will be higher in this particular method compared to your transfer learning with respect to multi-scale analysis. But once the the machine learning database is trained, then there are no more uh, challenges with respect to the speed of the method and how accurately C effective could be captured, so to speak. So we'll talk about that as well. And as in terms of multi-scale, you need a bunch of elements together, so that of course automatically comes to the part of assembly, matrix assembly, so to speak. And let me just check if there are any questions on this so far. Okay, Kumar Karthikeya from my organization says that he can hear and see, so that's good. So let me go back to where we were. So, so the next thing which comes to mind is the assembly part, right? So basically, so okay, it looks great that if there is an element which can capture the stiffness matrix of FEA accurately, captures its properties like symmetry, first is eigenvalues and stuff accurately, and then these things lie on the 45-degree line, the displacements lie on the 45-degree line. Uh, it means that we are getting somewhere. But then the next thing hits very quickly is about the assembly of these matrices. So when we talk about assembly of these elements, so I'm giving a 2D view because 3D will make things complicated. So first, let's understand it from a 2D perspective. So let's say this is a quad element, and then um, we can also make it 3D, so to speak. So now what you can see over here, so for example, let's name these nodes, number these nodes. So this is for example, the local node numbering. And let's say this starts at 9, 10, 11, 12, 13, 14, 15, 16. So basically, for this particular element over here, there are 8 corners, and this comes to metallurgists quite easily with respect to the solid 185 element, but then it's very similar for TET elements and things like that as well. So we'll go into TET elements later. First, let's try and understand this brick element. So there are 8 corners, and then there are, for example, 12 edges, and then there are 6 faces. So, for example, if there is another element, so we have this element, and let's say there is another element over here which just shares one of the corners. So there are, different combinations and permutations in which this element number one could be shared with other elements, like for example number two, number three, number four. So there are a set number of ways, synthetic combinations and permutations, in which this number one element will be shared by other elements. And if we can learn that trend in which this number one element will be shared at a corner with another element, at an edge with another element, at another phase with another element. So let's say if you are talking about a 3D element, your sub features in 2D, 1D, and 0D, they will be shared with other elements. And basically, whichever element it gets shared with, so for example, this gets shared at this particular node. So basically, let's say node number 2 gets shared with, let's say, node number 13. So node number 2 and node number 13 are getting shared, and it creates this kind of geometry, for example. So basically, that node number 2 and the previous will absorb the identity of the latter one. So node number 13 will not be there anymore. 13 will become 2, and then the stiffness contribution at 13 will be given to 2, and things like that. So basically, this entire thing will not be so since we are talking about 8 and 8, 16 nodes over here, or 48 DOFs, because these two entities will be merged. So basically, there will be 45 DOFs instead of 48 DOFs. And the way the different permutations and combinations in which two elements can be shared at the corner, um, two elements can be shared at the face, two elements can be shared at the edge. Those permutations and combinations become the base for understanding and learning how different in what different combinations and permutations that those particular nodes will be swallowed by other nodes of this particular element. So that will be also discussed in the latter talks, where basically we'll talk about how to learn the assembly of these finite elements in a way that a priori how this entire so basically, as a function of element shape and the material property, you will know the k accurately of all the elements, in a disintegrated fashion, meaning the nodes are not absorbed, or the nodes are not joined, or the identity of one element remains intact compared to the other one. So k1 and k2, as a function of its shape and function of material properties, will be known accurately. But then, as the two nodes kind of join together, or if you're talking about edges, like 4 nodes are joining together or 8 nodes are joining together on a face, different combinations and permutations of these node joining, we will learn. We should be able to create these databases, where synthetic stiffness databases from directly finite element method, where these elements will be joined with respect to one another, and then basically arrived at the global stiffness matrix value. For example, over here, if these are joining at this particular corner node, then instead of 48 DOS, you'll have 45 DOS, just because one has gotten absorbed. And basically, if we can learn that behavior, then the assembly, or the global assembly, becomes very, very easy. And that also gives us, this this training is both ways. So basically, if we have to, we'll have a a method of going from disintegrated chunks to fully assembled chunks. And since this in machine learning, you can invert the problem. You can go from fully assembled chunks to disintegrated chunks as well, and that's very essential, because when you are doing fully assembled and you're solving the multi-scale problem, for example, then you'll get the global stiffness matrix. But then the going back problem is seldom solved, where basically you are looking at a certain hotspot. So for example, if you're talking about a strength, going in the forward direction from lower length scale to higher length scale makes sense. But then the mechanics and how the disintegration takes place with respect to a global stiffness matrix to local stiffness matrices, where, for example, a hotspot of displacement is occurring, you need to have that inverse map with respect to stiffness matrices. And that inverse map can also be made available through this machine learning method. And we'll talk about it in terms of disintegration. So that is, and that disintegration is very, very useful, because in a way, what you're trying to capture is not only going in the forward direction and doing homogenization, but for heterogeneous problems such as fracture, such as damage, and other other mechanisms, metallurgical mechanisms, where basically the deformation is heterogeneous, localized, things like that, where there will be a formation of local hotspots. You want to come back from the global stiffness, from the global stiffness assembly to local. And on top of that, not only that, for example, you have a big chunk like this, where you're going from, sorry if this is not visible, maybe I should go to the next page. So basically, the other thing is, let's say you arrived at the global stiffness matrices from these local elements. You have k global as a function of k local, and that function is maintained. And you went from, let's say, solid 185 elements to the global stiffness matrix. What you also might want to capture is that when you're coming back, you may not be wanting solid 185 elements or quad elements. You might want tri or tet type of elements, tet higher order tet type of elements. So let's say if you're going back, and want to kind of go back in a dehomogenized fashion. I'm sorry, there's some echo going on. Wait a second. Okay. I hope everything should be fine now. Okay. Share again. Okay. And yeah, so the other thing which we also want to capture is, maybe while coming back, we want to come back in a tri or tet element manner. And it will be better, let's say the hotspot will be better captured if we come back in a different element sense compared to going forward in one element sense. So that those things will be also made much more simpler with this computer. All right, so that could be also dealt with. So basically, instead of coming back in this sense, you can come back, you know, in a different elemental sense, and maybe it could be a mix of two types of elements and things like that. So those relationships, generally speaking, we have this relationship available through finite element method as well, where k global is a function of k local, but what we don't have is how to get k local, f inverse of k global. So that is generally a harder problem in nonlinear problems, so to speak. Um, and that is another thing which makes perfect sense for dehomogenization and delocalization type of problems, because using machine learning, you can invert the machine learning function and also get what your k local, how your k local should look like. So these are some of the things which we would like to capture in the next few days and probably months, so to speak, during all my talks. And basically, the idea is, how to enable machine learning in order to make our finite element calculations faster. So, of course, you will see that in many cases you'll get exact matches in between your stiffness matrix which you compute from finite element compared to your machine learning element analysis. So for simpler problems, does it make sense? Maybe it doesn't make sense for simpler problems because the cost of generating the database might be higher than solving the problem directly using finite element analysis. But for complex problems where you have both material nonlinearity as well as the aspect of uh, different types of shapes, and and the other reason being some of the machine learning methods are pretty fast, and some of these machine learning methods, which we'll talk about in the next days and days, weeks, and months, is the other aspect of uh, some of these machine learning methods can also work with very limited data. So if that that becomes one of the issues for our customers or anybody who is practicing finite element, for example, they can weigh advantages and disadvantages, so to speak, of whether to train a machine learning element at the first place or not. But if they do train, then that machine learning element might be useful, um, uh, you know, uh, in a wide manner. And the other aspect is you just have to save the machine learning based weights and biases, and that should be all, because you don't have to uh, you know uh, redo this DOF loops, uh, double for loops with respect to finite element methods, so to speak, and generate the stiffness of each of these elements, so to speak. So we'll talk about, definitely for crystal plasticity, it makes quite a lot of sense because we have huge amount of material nonlinearity, huge amount of variables with respect to crystal plasticity, which might be useful from the point of view of creating a machine learning element and solve the problem much faster. But then also, for some other nonlinear laws where uh, you know uh, training is just one time affair, and you just save that weight and bias set and go anywhere you want. Uh, that might be a useful option in certain cases. Of course, you will get the best possible result using finite element method, but in certain cases, you'll see that some of the methods which we have employed, you'll get a very good match in between, let's say, displacements which you get from finite element with respect to a machine learning analysis counterpart. The other thing is how to quickly assemble the entire do the entire assembly very very quickly. So we'll also see that as you start solving bigger and bigger problems, assembly becomes quite a bit of a deal. So we'll talk also about how to accelerate this assembly using machine learning enabled methods. So let's say somebody wants to use finite element K, but want to do the assembly faster. So they can probably use this machine learning method to do the assembly faster. Or somebody wants to do traditional assembly, but you want to use the machine learning enabled element to populate their local elements pretty fast. That should be also an option. So we'll talk some of that aspects. Then the last part which we'll talk about is how to invert, locally, at your own will, and even if you have gone to the global K matrix using certain type of element, but since that that entire function has been derived using machine learning, the synthetic data contains other type of elements as well, and you can get back to the local stiffness matrix using the inverse of that machine learning enabled analysis, or that weights and bias function. So basically, you can invert your machine learning step and get back how the local stiffness matrices would look like, and that is very essential in case of de-homogenization, where basically you are looking at hotspots and localization of displacements and deformations. So we'll talk some more about that. And the first part, which is of interest from constitutive modeling, where how sensitive each variable is, we can compute using machine learning pretty fast. So basically, all the variables, for example, in this particular or a specific case of crystal plasticity, so to speak, you have lots of variables which control the behavior. But for different materials, your order and magnitude of different variables is different, and they affect the stress strain curves, or in a very very different manner, so to speak. So basically, how to create these machine learning networks where basically you can get the sensitivity out very very quickly, and once you have that the data trained, you just insert a new material, and based on that sensitivity, you would like to put more emphasis in getting that experiment done much more sophisticatedly, or maybe if the sensitivity of that particular parameter with respect to the stress strain curve or any other nonlinear parameter, for example, damage you're looking at, is not that high, then you will not put a lot of resources into getting that particular experimental parameter, so to speak. So basically, we'll talk about these three features in the days, weeks, and months to go. But I just wanted to kind of give a primer today about what we'll be covering, how it could make your life easier. And most of these methods, what we are trying to do is to enable finite element do even more, rather than run n number of finite element simulations and do the n plus one simulation using machine learning. So instead of doing that, we are just taking the approach where basically machine learning can help feed finite element strategies in a much better and accelerated fashion, and traditional methods can be presented in a 2.0 manner, so to speak. So that's it for today, and thank you for your time. I know this has been quite some time between my past talk and the current talk. I apologize again to a lot of academicians and industrial associates with respect to that. I intend to continue these talks in the future, and basically we'll talk one step at a time. So probably we'll start with this machine learning analog of the finite element method, followed by assembly, followed by the sensitivity of the parameters, so to speak. And then at the end, we'll probably look at some of the de-homogenization problems where, there is always a map from local to global, but then as a function of deforming elements and as a function of material nonlinearity, global to local is very hard to obtain. So we'll look into some of those aspects. So with that, I bid you adieu, and thanks for your time today. It is wonderful to share my opinions and share my state of mind with respect to what current work we are doing at ANSYS with respect to research and some of that, how it correlates with production. So we always try to make our latest and greatest available through papers and publications and conferences. So look out for talks and talks from our group in professional societies, so to speak, followed by any publications which we are continuously sharing with the wider group. Thank you for your time. And if there are any questions and concerns in the chat, I'd be very happy to answer. And again, my email is over here. Here's dipankar.pal at ansys.com. So please feel free to give me a holler about your questions and concerns, and maybe I learn from you. Most of the people, I talk to, have years and years of experience, or they're working on very innovative topics. So it's always good to hear and learn from you all. So thanks for your time today. Thank you. Have a great day. Bye.